Okay, Chapter 2, Section 2, the limit of a function. As we've seen already, studying calculus is a lot about studying what happens when 2 points get infinitely close to each other. So in this section, we're going to explore that a little bit more. So consider, for example, the following function. Let's investigate the behavior of the function f defined by f of x equals to x squared minus x plus 2 for values of x near 2. Okay, so let's graph this equation. I'm going to use Desmos again. Okay, so here is the graph of x squared minus x plus 2. And we're interested in seeing what happens as x approaches to 2. So as x approaches to 2, we plug in a 2 in here, and so we get f of 2 is equal to blank squared minus blank plus 2. And so we're going to be replacing the x value with a 2, so 2 there, 2 there, 2 there. And so we end up getting that f of 2 is equal to 4 minus 2 plus 2. These two cancel. And so we get that f of 2 equals to 4, or we get the ordered pair 2 comma 4. Right, so we want to investigate what happens around this point. So let's go back to this guy and graph that point. Here it is. When the input is 2, the output is 4. Let's zoom into there. There it is. When the input is 2, the output is 4. Okay, but what we want to do is investigate what happens as the input as x gets closer and closer to 2, without necessarily being equal to 2. That's an important distinction that we want to point out here. So let's say that we let x be some value near 2, somewhere over here, for example, and then explore what happens as we get closer and closer and closer, as we let x get closer and closer to 2. Okay, so that would look like this. As the input values get closer and closer and closer to 2, right? So here in this particular instance, x is equal to 3.254. But as we get closer and closer, as I slide this closer and closer and closer and closer and closer to 2, we see that the output value is also going to get closer and closer and closer to 4. And that's from either direction, right? So I can approach 2 from the right-hand side. I can go past it and approach 2 from the other direction as well. And we see that in either case, as x gets closer and closer to 2, then its output would get closer and closer to 4. Right? So we can see that clearly on here. We can also show this by using a table and our calculator. Okay, so go to quit, so second quit out of there, go to y equals, and then type in this equation, so clear there, and we end up with x to the power of 2, x to the power of 2 minus x plus 2. Okay, so here's that function, and then we're going to go back to table, so hit second table, delete all the previous values. Okay, and so remember that we're trying to approach 2. So we're trying to get close to the value of 2. So if we approach it from the right-hand side, we can go from 4 down to 3, down to 2.8, 2.6, 2.4, 2.2, 2.1, 2.01, 2.001. As you can see, we're getting closer and closer and closer to an output of 4. But we can also approach it from the other direction. So now if x is on the other side of 2, and we are approaching, getting closer and closer to 2, so say we go from 0 to 1 to 1.1, 1.2, 1.3, 1.7, 1.9, 1.99, 1.999. Okay, so we're getting closer and closer and closer to 4 from either direction. Okay, so here's a table that has those values, right? When x is equal to 1, the output is 2. When x is equal to 1.5, the output is 1.75, and so on and so forth. So we're slowly getting closer and closer to 2. X is getting closer and closer to 2, and the output is getting closer and closer to 4. Same thing from the other direction. X is equal to 3, then 2.5, 2.2, right? So we're slowly walking closer and closer and closer to 2, and so we see that the output is getting closer and closer to 4. So here's a nice little image of that. So again, this is our parabola. Here's the equation, x squared minus x plus 2. We see that as we let x get closer and closer and closer to 2 from either direction, the output of that function is going to get closer and closer and closer to 4. I know that right now there's a strong temptation to just want to put in a 2 in there and be like, okay, why don't you just put a 2 in there and be done with it? But that's not the point of this. The point of this is to show that as we let the input values get really, really close to 2, the output values are going to get really, really close to the desired result here, the 4, right? Okay. So, in fact, it appears that when we make the value of f of x as close as we like, in fact, it appears that we can make the value of f of x as close as we like to 4 by taking x to be sufficiently close to 2. So in other words, if we look at this in reverse and we go, okay, well, what's it going to take to get really, really close to 4? Like, I want to be within 0.1 units of 4. Let f of x, I want to figure out what value of x would result in a output value that's incredibly close to 4. Then you can kind of reverse engineer this and go backwards and figure out how close the input needs to be to 2 so that the output is sufficiently close to 4. Right? It appears that we can make the values of f of x as close as we'd like to 4 by taking x to be sufficiently close to 2. Okay? We can express this by saying that the limit of f of x equal to x squared minus x plus 2 as x approaches 2 is equal to 4. Right? And notation-wise, we adopt this notation. This limit, the limit as x approaches 2, right? The input is approaching 2, of our function is going to be equal to 4, right? And so at this point, this is achieved by looking at our graph. Hopefully it makes sense from the graph, and also by using our calculator and letting x get incredibly, incredibly close to 2 until we see a pattern and we feel comfortable concluding that that must be the answer. What you are not allowed to do at this point, as you do your homework, this is not about plugging in a 2 here. Right? This would be wrong. At this point, if all you do to find this limit is put 2 there, and that's how you get a 4, then you're missing the whole point. Right? It's not about evaluating this function at 2. It's about evaluating this function at values really close to 2 on either side of 2, getting infinitely close to it, seeing a pattern, and being able to determine what that limit is going to be based on that pattern. Right? If you're wondering, well, why don't you just put a 2 in there? Well, because this process allows us to find the limit in cases where you're not going to be able to just plug in that value, as we will see in just a minute. Okay, so now we have a nice formal definition of limits. So the limit of a function, in general, we can use the following notation. The intuitive definition of a limit. Suppose f of x is defined when x is near a number a. This means f is defined on some open interval that contains a, except possibly at a. Right? So that's an important distinction here. The limit doesn't matter what the actual value of x equals to a is. We want to consider cases where x is getting infinitely close to a, but not necessarily at a, right? So the limit as x approaches a of f of x equals to L, and we say that the limit of f of x as x approaches a equals L. If we can make the values of f of x arbitrarily close to L, or as close as we like, restricting x to be sufficiently close to a on either side of a, but not equal to a necessarily. Okay, so let's draw a little picture of what all this means here. Okay, so let's say that we have this function f of x just arbitrarily drawn to look like this, and we're interested about the limit as x approaches to a. So let's let a be some value in the domain of f of x, and so therefore it maps onto f of x, and so we have f of a equals to L. So what we're saying is that what we're going to do is we're going to create a little interval around a. And so we're going to say let x be a value near a, but not necessarily a itself. So x is going to be something chosen inside this little window. Any number inside here, anything in there can be selected, except maybe a. Okay, so now we're going to pick some value of x that's arbitrarily close to a, so somewhere in this little interval. So let's say x is just, maybe that value right in there. So x is some value chosen near a. It will then map some value there, which will then map to some value over here. And so we'll have some f of x value over here. Okay, so that should be the information, a picture that can kind of follow this here. So f of x is defined when x is near the value a, right? But except maybe possibly at a. So it's possible that f of x might not even be defined at a. It might be defined at x equal to a. It might not. This might have a little hole there actually. But that's okay. We don't really care about the actual value when you plug in a into our function. What we care about is what happens as we let x get closer and closer and closer to a from either side, as we choose different values along this little neighborhood and we get closer and closer and closer and closer to a. What's going to happen to our output? Well, our output, as you can see, is going to get closer and closer and closer to L. If we had chosen some other value over here, like let's call that x sub 1, maybe this one's over here is x sub 2, so maybe this one maps to there and then comes over here. Maybe this is f of x sub 1, and over here we have f of x sub 2. And as you can see, the closer we let x be to a, the closer that the output of f of x's, whatever those outputs are, the closer they will get to L. Right? So that's what this is saying. The limit of f of x as x approaches to a equals to L if we can make the values of f of x arbitrarily close to L, or as close as we like, by restricting x to be sufficiently close to a on either side of a, but not necessarily equal to a. Okay, so hopefully that makes sense. Alternatively, right, instead of this notation, this is a very popular notation, but another very popular notation is to think of it this way, that the f of x approaches to L as x approaches to a. Right? The f of x will approach L as x approaches to a. Okay, so here's some graphs that will depict that. Let's see. So these are similar. Notice that here we have some function f of x. These are all f of x functions. So this is some f of x or some f of x. So these are just random examples of functions. And notice that in the first case, the function is defined at a. F of a does in fact equal to L, and it's right on that curve there. Over here, f of a is defined to be something, but it's not equal to L. It's equal to something else, right? And then over here, f of a is not even defined, right? So here, f of a does not equal to capital L, but it is defined. Whereas over here, f of a is not defined, does not exist, right? But we don't really care. No matter what happens, no matter which one we're talking about, the limit is going to be the same for all three cases. We don't care about the value of the function at a when we're trying to consider the limit. We're trying to figure out what happens to the limit. So as x gets closer and closer and closer to a from either side, we see that the output values are going to get closer and closer and closer, closer and closer and closer to capital L. So the output values of f of x will get closer and closer to L. Okay. So the limit is going to be L for all three cases. As x approaches to a, as x approaches to a, for all three cases, no matter what, the output values are still going to be getting closer and closer and closer to this L, which means that f of x will squeeze in toward L in any case, right? It doesn't matter what the actual value of the function is at that point, right? Independent of that, f of x will approach L, f of x will approach L. So no matter what, the limit as x approaches to a of f of x equals to L. Okay, let's consider this example. Let's find the value of the limit as x approaches to 1 of x minus 1 all over x squared minus 1. Right? As I mentioned before, there's this strong desire to want to just plug it in there, and this is exactly why you can't think of it that way. Because note that if we just plug in a 1, we end up with blank minus 1 all over blank squared minus 1. And then if we just plug in x equals to 1, we end up with 1 minus 1, which is 0, divided by 1 squared minus 1, which is 0. You just get a 0 over 0, which is undefined. Not useful, right? So we can't just plug it in there. Luckily, finding a limit has nothing to do with plugging in a 1, at this point at least. There will be cases, I know some of you guys have already peeked ahead and maybe you've had these classes before, so you know that there are some situations where this is okay, but for now we haven't looked at any of those, so we just have to stick to our basic description of a limit, and you know, our method for finding it is going to be to evaluate this at values that get closer and closer and closer to 1. Okay, so what we want to do is just good old-fashioned table. We're going to have a table where we have x values, and then we have these results. I want to have f of x equals to x minus 1 over x squared minus 1. And I want to input values get closer and closer and closer to 1 without ever actually being 1. So maybe we start at 3, 2, 1.9, 1.7, 1.4, 1.3, 1.2, right? We slowly walk toward 1 and see if there's a pattern. From that pattern, we'll be able to establish what this limit is. So 1.1, 1.01, 1.001, and so on and so forth. Okay, so let's get our calculator out. We definitely don't want to do this by hand the entire way. So we're going to plug this into our calculator and use the table form to figure out what these results are. Okay, so go to y equals, clear, and we want to type in this. So be careful with your parentheses. The numerator is going to be x minus 1, close parentheses, divided by, open parentheses, x to the power of 2 minus 1, close parentheses. Here's our equation. We can go back to table, second table, delete all the other previous values, and then let's figure out what this is. Starting at 3, we get that, then maybe 2, then maybe 1.9, 1.7, 1.4, 1.3, 1.2, 1.1, 1.01, 1.001. Okay, so we start to see a pattern. It looks like as we get closer and closer and closer to 1, starting from the right-hand side, starting from the larger numbers and walking down toward 1, but never actually equal to 1, it looks like I'm getting really, really, really close to 0.5. It seems to be walking that way. Again, notice that if I put a 1, I'm just going to get an error. Right? Plugging in a 1 gets me an undefined. All right, let's walk toward 1 from the other direction. So if I start off at -2, -1, 0, 0.1, 0.2, 0.4, 0.6, 0.8, 0.9, 0.99, 0.999. There. Okay, so again, we start to see a pattern that we get as we let the input values get closer and closer to 1, starting from the left-hand side, starting from numbers that were strictly below 1, and walking my way toward +1 without ever letting it be actually equal to 1, we start to see a pattern appears. And again, from both directions, it's approaching 0.5. So that's how I know that this limit is going to be equal to 0.5. Here's a little table of showing the same thing. As we let x equal to a variety of numbers, slowly creeping up toward 1, but never actually equaling 1, we see that the output values get closer and closer and closer to 0.5. And same thing from the other direction, as x is slowly growing down toward 1, never equaling 1, we see that the output values get closer and closer and closer to 0.5. So from this, we can infer that the limit as x approaches to 1 of x minus 1 all over x squared minus 1 is equal to 0.5. And here's a graph for it. If we graphed it, we would see that it looks just like this, and of course there's a little hole there because it's undefined. This function is undefined when x equals to 1, right? That's why there's a little hole there. Note that f of 1 is undefined. Good, but that's okay. We were able to figure out that its output is going to be the limit is going to be equal to 0.5, right? By slowly walking through that process. In fact, if we just manipulate this same question by just a little bit and redefine it this way, let g of x be a function defined by this same equation for all input values other than 1, and then separately we defined that whenever x does equal to 1, its value is equal to 2, well then we'd end up with a graph that looks almost identical, except we'd have a little dot there, right? When the input is 1, the output is 2, so we have a little value there, but the limit stays the same, right? So the same thing happens here. The limit as x approaches to 1 of g of x is still going to be equal to 0.5. All right, let's try another one. Okay, how about this one? The limit as h approaches to 0 of the square root of h squared plus 16 minus 4 all over h. Again, note that if we let h equal to 0, if we just plug that into there, we'd end up with something squared plus 16, square root of that, minus 4 all over something go there. So if we let the h just be a 0, if we just plug in a 0 into there, we would end up with the square root of 16 minus 4 all over 0, which again gives me a 0 over 0, which is again undefined. Right? So it doesn't do us any good to just plug in a 0 in this case. So if we want to find the limit, what we have to do is plug it into our calculator and let values of h get closer and closer and closer and closer to 0 so that we can figure out what this limit is. Okay, so in order to plug it into my calculator, I'm also going to manipulate this a little bit. I'm going to say that the limit as h approaches to 0, it's an h, is equal to the square root of, is equal to the square root of h squared plus 16 minus 4 all over h is the same thing as the limit as h approaches to 0 of parentheses h squared plus 16 to the power of 1/2 minus 4 all over h. And to the power of 1/2, for the purposes of my calculator, I'm going to change this to 0.5. Okay, so let's get our calculator out. Y equals, clear, okay, so it'll be parentheses, and then instead of h, we know we use x, so x to the power of 2 plus 16, close parentheses, to the power of 0.5, so that's the same thing as the square root of x squared plus 16. And then minus 4. Okay, so I messed up because I want to put this whole thing all over in the numerator. So I'm going to have to come back here at the very beginning. So let's go back over here and put insert. So second insert, and then I can put that extra parentheses there. Okay, and now I can go back to the end, close parentheses, divided by, and then finally another x. Good. Enter. Good. So now I have my equation. I can go back to table. Second table. Let's delete all those values. Okay, so we're interested in values near 0. So let's plug in values. So say starting at 2. This would be the result of replacing each of these with a 2, right? So 2 squared would be a 4, plus 16 would be 20. This would be the square root of 20 minus 4 all over 2, and that's the decimal answer we would get. Okay, so let's try getting closer to 0. How about 1? How about 0.8? How about 0.6? How about 0.4? How about 0.2? How about 0.1? How about 0.01? About 0.001? Okay, so it looks like it's getting really, really small, really, really close to 0. Okay, all right, how about if we approach it from the other direction, from the negative side? So let's go over to the other side and plug in negative 3, negative 2, negative 1, negative 0.8, negative 0.6, negative 0.3, negative 0.1, negative 0.01, negative 0.0001. Okay, looks like they're always negative, but they're getting really, really, really small, really, really close to 0. So from both patterns, from both directions, it seems like this limit is approaching to 0. So based on my calculator work, I feel confident in coming back over here and concluding that this limit, the limit as h approaches to 0 of this function, is going to be equal to 0. Same thing as this one, equals 0. Let's graph it and confirm. See what we get. Okay, so here is the graph of the function we're dealing with. Let's zoom in. Here it is. And if we start okay, and so as we let the input value of x start getting closer and closer and closer and closer and closer to 0, we see that the output value is in fact going to be getting closer and closer and closer and closer to 0, but always positive. And if we approach it from the other side, we see that as we input negative values that are getting closer and closer and closer to 0, we see that the output values of this function are getting closer and closer and closer to 0. Always negative, always some small negative, but we can see that they are in fact approaching 0. What isn't terribly clear about here is that the function itself is not defined at 0, right? If we tried to find f of 0, it's going to give us an undefined, right? We can't evaluate it at 0. So it's not entirely clear here, but there's like a little hole there because it's not defined at 0. All right, let's try a different one. This is a very, very popular one in calculus. So consider this. Let's find the limit as x approaches to 0 of sine of x over x. Right? So now if we think about the graph of the sine function, the sine function is going to look like this. It starts off at 0, comes up, comes back down, and here's one period of sine. And then in the other direction, it's going to do the same thing. It's going to come back, and go this way like this, right? So here is f of x, here is x, and then this is the sine function, sine of x. So we could see that as I choose values of x that are getting closer and closer and closer to 0 from either direction, as they get closer and closer to 0, the output values are going to get closer and closer to 0 for the numerator. Right? So as x approaches to 0, from either side, the numerator is going to approach to 0. And, well, the denominator is just x, so that's also approaching to 0. So again, if you attempt to just plug in a 0, bad things are going to happen. Note that sine of 0 over 0, if we just let x equal to 0, put a 0 there, put a 0 there, we're going to end up with sine of 0, which is 0, all over 0, which is, again, undefined. Not helpful. Okay, so the only way to figure out what this is going to be for us to use our table function in our calculator, plug in values that get close to 0 from either direction, and then seeing if there's a pattern that's established. Okay, so let's use our calculator. Now, let's quit out of here. Second quit. Let's go to mode, since this is the first time we're using trig functions. Let's make sure that we are in radians, right? By default, you should work with radians unless unless it's specified that you should be working with degrees. But a lot of equations work really well with radians. Okay, so make sure you're in radians. Normal, float, everything looks good. Just make sure you're in radians. Let's get out of here. Let's go back to y equals. Let's clear this out. And we want to put sine of x in the numerator divided by another x. So sine of x over x. there's our function. And let's go back to table, delete everything here. Okay, so again, we want to get close to 0. So let's plug in a 2, for example, plug in a 1, plug in a 0.8, plug in a 0.6, plug in a 0.4, plug in a 0.2, plug in a 0.1, a 0.01, a point, oh, okay, well, it looks like it's a solid 1 there at that point, but that's because our calculator is already rounding. So if you use your arrows to highlight that point right there that says 1, in fact, it says 0.999, 4 nines and an 8333. Okay, so that's the value. It just doesn't fit in this little box here, so they just round it to 1. So we can see we're getting really, really close to 1 from that direction. Let's attempt it from the other direction. So we were always putting values that were positive and then walking towards 0 from the right-hand side. Now let's walk towards 0 from the left-hand side. We start plugging in -2, then -1, then -0.8, then -0.6, then -0.4, then -0.2, then -0.1, then -0.01. Okay, well at this point it's already rounding again, so we can use our arrows and go there, and we see that it's not really a 1, it's this long decimal, right? Okay, and again, if we just try and plug in an actual value of 0, we're going to get an error. So we can't just plug in a 0. We have to use this process of walking our way toward that value so we can see what it's heading toward. And so since we did it from both sides, both directions, I feel sufficiently confident in concluding that the limit must be 1. So this isn't a formal proof, we'll get to that later, but for now, I feel pretty confident in saying that this limit must be equal to 1. Let's graph it and confirm. So let's say that we go over to Desmos now, and let's change this again. Let's change this to x again, x. Okay, and so here is what the graph looks like. Zoom out a little bit. This is what sine of x divided by x looks like. So it's got that up and down wavy kind of pattern of a sine function, except that it seems to be tapering down toward the x-axis. Right? As we walk this way, it seems to be getting closer, so that's interesting. And then right around 0, as the input values get closer and closer and closer to 0 from either direction, from this direction or from this direction, in either way, it looks like the output of that function is getting really, really close to 1. Right? Remember that technically there's like a little hole here, right? Because this function is not defined at 0. If we try and plug in a 0, we're going to get an undefined. So this is a little bit misleading. It almost, we can't really tell that there's a little hole there, but we can see that it's heading toward 1. So, so far in this section, if you want to find the limit of something, one thing you could do is just graph it. So great, just graph this and see where it's heading. So we can see that it's heading toward 1 in either direction. Remember that 100 years ago, before we had computers, it was really hard to graph these things. So they had to come up with alternative ways, a more algebraic way of finding these things. And also there's a larger purpose for doing it this way. So just trust in the process. Do it by using the table format in your calculator to find the limits in this section. All right, let's move on. All right, let's try another very famous example from calculus. The limit as x approaches to 0 of sine of pi over x. Right, so find the limit as x approaches to 0 of this. Okay, so let's consider the following. Let's say we let x, here's our number line, here's our x-axis, and here's 0. So we're going to approach 0, and I'm going to pick the following path to get there. So first I'm going to think of like maybe 1/2, and then I'm going to go to maybe like 1/3, and then I'm going to go to like 1/4, and so on and so forth as I approach 0, right? This pattern is approaching towards 0. And let's look and see what happens to each of those values. So if I have sine of pi over blank, and then sine of pi over blank, and sine of pi over blank, and so I'm going to put a 1/2 right in here, and I'm going to put a 1/3 right in there, and then I'm going to put a 1/4 right in there. Okay, so multiplying the numerator times the reciprocal of the denominator makes this simplify to sine of 2 pi. And that makes this equal to sine of 3 pi, which then makes this equal to sine of 4 pi. And if we remember our graph for the sine function, right, our graph of a sine function, so here's our sine function. And notice that right there, here's our sine function. Notice that when I plug in pi, we get a 0. When I get 2 pi, I get a 0. When I get a 3 pi, I get a 0. 4 pi, 5 pi. So all the multiples of pi are going to be equal to 0. So all of these are 0. So all of these equal 0. And I know that for any multiple n, I'm going to get a 0. So I know that if I continued this pattern, if I let this be sine of n pi for any counting number n, then I know that that's going to be 0. And so kind of reverse engineering this over here, I know that if I pick something that looks like this, all over 1 over n, anything that looks like this, let's put this in blue. Anytime I plug in x equals to 1 over n into this function, I'll be able to get something that fits this form and then equals to 0. So then it might be tempting to conclude that the limit as x approaches to 0 of sine of pi over x, that equals to 0, right? It would be tempting, but this is actually wrong. That's not true. Why is that? Well, I have found one path towards 0. If I let x equal to 1/2, so if x equals to 1/2, comma 1/3, comma 1/4, comma 1/5, comma dot 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 dot, I have found one path towards 0 where all the outputs lead to 0, right? When I let x equal to all of these values, in every single one of these cases, the output is going to be 0. So it makes you think that it's always 0. But note that there is another path I could take. Let x equal to 2/5. What happens at 2/5? So if we let x equal to 2/5, then my sine function, sine of pi divided by 2/5, is equal to sine of 5 pi over 2 and sine of 5 pi over 2 is equal to 1. Right? This is the same thing as sine of 4 pi over 2 plus pi over 2, and this is just 2 pi. This is equal to sine pi over 2. So sine of pi over 2, we know that's equal to 1. Right? If we graph the sine function, here it goes up and then comes back down. Here's your standard sine function in the first period. And here is pi over 2. That leads to 1. And so if I just extend that and add another 2 pi, so here's the end of the first period of sine, and then it begins to repeat itself. So if I add from here to here, if I add to this 2 pi to it, I will end up at 5 pi over 2. This point right there will be 5 pi over 2. And so it will also lead to a height of 1. In fact, if I add another 2 pi after that, I will also get to another value that equals to a 1. So if I add another 2 pi to this, I'll end up at the following. Sine of pi over 2/9, that will simplify to give me sine of 9 pi over 2, which is equal to sine of 8 pi over 2 plus pi over 2. And this is equal to 4 pi. This is sine of 4 pi plus pi over 2. Right? So that's this same thing. We start here at pi over 2, and now we're going to add one multiple, another multiple of 2 pi, and that'll get us to another place, well, that'll get us to another point over here that's going to be equal to 9 pi over 2, 9 pi over 2. And I can tell that that's also going to be another case where the output is equal to 1. Right? So what I've established here is that if I follow another path toward 0, if I let x be equal to 2/5, and then I let x equal to 2/9, and then I let x equal to 2/13, and then I let x equal to 2 over 17, and so on and so forth, and so on and so forth. What I've done is I found another path that's leading towards 0, where all the outputs are going to be equal to 1 with our function. Right? So one path is this one, 1/2, 1/2, 1/3, 1/4, 1/5, and yet another path would be to let x equal to 2/5. So let's say that one. 2/5, and then it equals to 2/9. It's going to be like over here, 2/9, and then x equal to 2/13, and so on and so forth. So both paths lead to x growing towards 0, but in one case, all those inputs lead to an output of our function of 0, and in another case, all those outputs of our function lead to a 1. So what is this saying? Let's look at the graph. The graph might bring some light to this. So let's look at the graph of this function. So this is the graph of sine of x. So let's graph f of x equal to sine of x, sine of pi divided by x. Oops. Here's what the graph looks like. Let me zoom in a little bit more. So here's what the graph ends up looking like. Notice that there is a particular choice of x values, right? So if I stick to a particular pattern of letting my x values equal to a certain path, let's graph them. So we had, let's graph the point 1 divided by 2, comma 0. That would be that point. 1 divided by 3, comma 0, that would be another point, and then 1 divided by 4, comma 0, 1 divided by 5, comma 0. Okay, so what we should be getting out of this is that if I choose these points as I walk toward 0, if I walk toward 0 in a particular path, the outputs are always 0. And there's an infinite number of values as I walk closer and closer and closer to 0. I can let x be any number of the form 1 over n, where n is a counting number, and the outputs of my function are always going to be 0. Right? On the other hand, there's a whole other path I could take. I can choose specific values of this function where I let it be equal to the path of 2 divided by 5. Path of 2 divided by 5. So if I let x equal to 2 divided by 5, notice that that's going to be the x value is somewhere in here, and I get this point over there. And now if I let x equal to 2 divided by 9, comma, f of 2 divided by 9, again I get this point up here. Right? So I can cherry pick a very specific order of values of x so that the output of my function is always going to be 1. I can very specifically choose values of x so that my output is always 0. And in fact, we could do the same trick for any value between -1 and 1, because the graph does not head toward a specific number. The output of my function does not head to a specific output as the input grows towards 0. The function begins to oscillate back and forth uncontrollably as I get closer and closer to 0. Right? So if I zoom into here, you see that in fact it just oscillates more and 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 more, an infinitely number of times. So it almost looks like a dark shade there. That's because it's oscillating so fast between -1 and 1 that it might give us the wrong impression. Okay, so what's the real answer? This is a case where the limit does not exist. And it does not exist because it doesn't satisfy the very specific definition of a limit. Remember, what we want is a case like, a simple case like this one, where as the inputs get closer to 0, no matter what path I take, no matter which choices I make, as the inputs get closer and closer and closer to 0 from either direction, the outputs get closer and closer to 1 from either direction, right? So this is a case where the limit does exist. That was the sine of x over x case. The limit equals to 1 as x approaches to 0. But in this case, as the inputs get closer and closer to 0, the outputs are actually oscillating back and forth, back and forth, back and forth. They never agree, they never come close to a specific point. They always oscillate back and forth between -1 and 1. Therefore, the limit does not exist. The tricky thing about this one is that you can trick yourself into thinking that it does converge to something, that it is heading toward a specific output based on the inputs you choose. If you choose a specific pattern, then the outputs will head towards 0. If you choose another pattern, then the outputs will go toward 1. You can also pick a specific pattern where the outputs all head toward -1 or positive 0.5, or any other number you choose between -1 and 1. Okay, so the answer to this one is that the limit as x approaches to 0, the function sine of pi over x does not exist. All right, now let's take a look at one-sided limits by considering the following function. Let h of t be equal to 0 if t is strictly less than 0, and let h of t be equal to 1 if t is greater than or equal to 0. So let's find the left and right limits to this function. Let's graph it. It's a straightforward, easy graph to sketch at least. So for values when t is strictly less than 0, the output of this function is going to be 0. So we're going to have a little hole there, and then it's a solid blue line that way. And when t is greater than or equal to 0, then we're going to have a solid 1 there, something like that. This is at 0, and this is at 1. Okay, so let's consider the limit. The limit as t approaches to 0 of h of t. As we choose values of t that are getting closer and closer and closer to 0, so let's say we choose this value there, and we get closer and closer and closer, we see that the output values are going to be approaching to 1. And when we choose values of t in this direction, I get closer and closer and closer and closer to 0, we see that the output values approach 0. So they don't agree with each other. We would say that the limit as t approaches to 0 of h of t does not exist. Okay? Because they don't agree with each other. From one direction, if you approach t from one direction, the outputs are 0. And when you approach 0 from the other direction, t values are always positive. You approach it, they approach 1. So we would say that the limit does not exist. However, we can salvage this situation by at least restricting how we approach 0. So obviously, if we approach 0 from the right-hand side, so always bigger than, but are getting smaller, so that this is what we consider approaching it from the right-hand side, then we see that the outputs are always going to be 1. So the limit does exist in that direction, and same thing from the other. So the way we want to describe that is by saying the limit as t approaches to 0 from the left-hand side. That little upper right-hand side, little minus side, means that it's from the left-hand side, h of t. And then we're also going to have the limit as t approaches to 0 from the right-hand side of h of t equals. So this is from the left side, while that guy right there means from right side. Okay? And we can see from here that from the left, if we approach, t approaches to 0 from the left side, the outputs of our h of t function are always equal to 0, so that's what this limit is. The limit is 0. It doesn't matter that at t equals to 0, the output is actually 1, not 0. It doesn't matter. The limit is about what it looks like. Where does it look like it's heading? And it looks like it's heading toward 0. On the other hand, as t approaches to 0 from the right-hand side, we see that it gets, as t approaches to 0 from the right-hand side, the output values are always equal to 1. So this is going to be equal to 1. Okay? We still say that the limit, if we don't put a condition, if we don't put a restriction here, this is an unrestricted limit, then this notation is saying you can approach it from any direction, every direction, and you should get the same result if it exists. But clearly we don't get that. That's why if we just simply say the limit as t approaches to 0, the answer is does not exist. But if we at least restrict our approach and say find the limit as t approaches to 0 from the left-hand side, then the limit does exist and it's equal to 0. And if we again restrict our approach to say that we're going to let the t value approach to 0 from the right-hand side of our function, then the limit does exist and it's equal to 1. Good. Notice that for this graph, that means that h of 0 itself does equal 1. Right? When the input value is exactly equal to 0, we follow these instructions. Okay, so let's put that in general. So we have a new definition for one-sided limits. The limit as x approaches to a from the left-hand side, right? Remember that this little guy up here, this little guy here means that it's from the left-hand side. The limit as x approaches to a from the left-hand side of f of x equals to L, and say the left-handed limit of f of x as x approaches a, or the limit of f of x as x approaches a from the left side is equal to L if we can make the values of f of x arbitrarily close to L by taking x to be sufficiently close to a with x less than a. Right? Again, note that for all of these, the result of the limit is independent of the actual value of the function at x equals to a. Right? It might be defined there, it might not be defined there, but the limit doesn't care about that. We care about what happens as we get closer and closer and closer to that value. Okay, so the left-hand limit requires that our x values that we choose are always going to be to the left of this value on the number line, right? So they're always going to be less than a. On the other hand, we can define the right-hand limit. Similarly, if we require x to be greater than a, and then we're approaching a from the right-hand side, then we put a little plus sign right here to indicate that this is from the right-hand side. The limit as x approaches a from the right-hand side of f of x equals to L. If it's true that we can make the output f of x arbitrarily close to L by selecting x to be sufficiently close to a, but always to the right-hand side of it, always greater than a. Okay, so here's a couple of nice pictures to depict that. So here we have some sort of a function f of x, and then here is a, and it doesn't matter what that function does to the right of a. Maybe the function just stops there, maybe it continues, maybe, it doesn't really matter. If we're only considering what happens as x approaches to a from the left-hand side, then this is all we need to know. Okay? So we can see from this picture that as x approaches to a, the output values are getting infinitely close to the value of L. So translating that over here would say that this is the value L, and then here is f of x, and so f of x is getting arbitrarily close to L as x approaches to a from the left-hand side. Good. Similarly over here, this translates into my L there, and if I have some f of x value there, f of x is getting arbitrarily close to L. The outputs of the function are getting arbitrarily close to L as x approaches to a from the right-hand side. So that's why we have those little plus signs. From the left-hand side, from the right-hand side. Okay, hopefully that makes sense. By comparing definition 1 with the definition of one-sided limits, we see that the following is true, that the limit, the unrestricted limit, right, no plus or minus there, the unrestricted limit as x approaches to a of f of x equals to L, if and only if it's true that the limit from the left-hand side is equal to L, and the limit from the right-hand side is equal to L. So the unrestricted limit is more powerful. It's saying as x approaches a from any direction, either side, the limit as x approaches to a of f of x equals to L, we can only say this statement if and only if it's true that both of these two statements are true, right? So these should be together. These two together, if I can show that those two are true, I can then conclude that this one must be true, or back and forth. If this is true, it must be that this is true. If this is true, then this must be true, right? And so if the left side limit of f of x equals to L, and the right-hand side limit also exists and it equals to L, therefore they equal to each other, then we can conclude that the unrestricted limit exists and is equal to L. Here's a nice example where we are given a graph. So here's a nice graph of g of x. We don't have to worry about the equation of g of x. Here's just its graph. And based on the graph, we can find all of these limits. So the limit as x approaches 2 from the left-hand side of g of x. So here is 2. As x approaches 2 from the left-hand side, we're going to have x approaching 2 from this way, right? So we're choosing x values approaching this way. And as we're approaching from the left-hand side, we see that the output values are heading toward 3. So that's the answer to that, 3. Okay, the limit as x approaches to 2 from the right-hand side. So now if we choose values of x that are there, and then there, and there, and there, and there, and there, and there, and there, as x approaches 2 from the right-hand side, we see that the output values are heading toward 1. So that's the answer to that one, 1. Okay, the limit as x approaches to 2 of g of x. Okay, so it's unrestricted. So you're supposed to be able to choose values from here. Like let's say I choose that one as my first value, and then that one as my second value, and then so on and so forth, back and forth, heading from either direction. And as you can see, in one direction, I was heading toward 1. As I pick values that are a little bit larger than 2, I'm going to be starting to head toward 1. As I pick values that are heading toward 2, but always a little bit smaller than 2, it looks like my outputs are heading toward 3. So the limit does not exist. Does not exist. The left side limit exists, it equals to 3. The right side limit exists, it equals to 1, but they don't equal each other. Therefore, the unrestricted limit does not exist. Okay, let's try the others. Now let's consider 5. As we find the limit as x approaches to 5 from the left-hand side. So if we choose values that are to the left of 5, and then we get closer and closer and closer and closer and closer and closer to 5 from the left-hand side, we see that the output values look like they are approaching 2. So that's what this is. It equals to 2. Now if we start choosing values that are to the right of 5, so there, right? So all these values always approaching 5, getting closer, closer to 5, but always larger than 5, then the limit as x approaches to 5 from the right-hand side is also going to be equal to 2. And now the unrestricted limit, the more powerful statement of just saying let x approach 5 from any direction. I can choose an x value over here, I can choose an x value over there, I can choose one over there, it doesn't matter. As long as I'm getting closer to 5 from any direction, then I'm considering the unrestricted limit. And no matter how you're approaching 5, it looks like you're always heading toward 2, so the limit does equal to 2. So the left-hand limit exists, it equals to 2. The right-hand limit exists, it equals to 2. They equal each other. Therefore, the unrestricted limit as x approaches to 5 does exist, and it equals to 2. Okay? Note that g of 5 looks like g of 5 equals to 1. Right? Nothing wrong with that. Has nothing to do with the limit. Right? The limit cares about what it looks like. Where does it look like it's heading, not what it actually is at that value. Care more about what it looks like. Where does it look like it's heading? Okay, infinite limits. Let f be a function defined on both sides of a, except possibly at a itself. Then the limit as x approaches to a of f of x equal to infinity means that the value of f of x can be made arbitrarily large, or as large as we please, by taking x to be sufficiently close to a, but not necessarily equal to a. Okay, so another notation for this, the limit as x approaches to a of f of x equals to infinity is often this, that f of x grows toward infinity as x grows toward a. Okay, so again, the symbol, this little infinity symbol, is not a number, right? It represents a direction, right? It's growing. But the expression, the limit as x approaches to a of f of x equals to infinity, is often read as the limit of f of x as x approaches a is infinity, or f of x becomes infinite as x approaches to a, or f of x increases without bound as x approaches to a. I prefer this one myself, f of x increases without bound as x approaches to a, but they all mean the same thing. And in different parts of the textbook, I think you'll find that they make references to all three of them. Okay, so here's some pictures of what all that means. So here, the actual function is the blue one. So the blue one is this guy, and then as x gets closer and closer to a, right, so as we choose an x value here, and then here, and then here, and here, the output values are going to start to grow out of control, right? And they never stop growing. This goes up toward infinity. I can make the output value, right? This guy right here is the f of x values. So let's say this is f of x sub 4, and this is some x sub 4 here. So as I choose this value, the output is there, and that gives you that. I can make it even higher by choosing a value that gets even closer to a, even closer to a. So I can get my outputs to get arbitrarily large as long as I let my x get arbitrarily close to a, right? So it's an unrestricted limit, so it grows toward positive infinity as long as x approaches to a on either side. Note again that this is a case where the actual value of x equals to a is not a valid input value. It's not in the domain of this function. We're going to get an undefined if we let x equal to a and plug it into there, right? F of a is undefined, right? There is no blue curvature. This doesn't curve anywhere this way. It just keeps growing out of control. So the limit as x approaches to a of f of x equals to infinity, or we would say that the output, the f of x function, grows toward infinity as x approaches a, right? Either one of those is fine. We also have the other direction, of course, that the f of x function could be growing down toward negative infinity as x approaches to a from either side. This is the unrestricted limit. So as we choose values of x, like say x is there, okay, well, that's going to map to that one. I pick another x value, well, that's going to map to that one. I pick this x value, that's going to map to that one. And as I get closer and closer and closer and closer to a, my output values are going to start to head toward negative infinity. Of course, it's unrestricted, so you get to choose them from either side. So either way, as x approaches to a, from either side, my output values of my function are going to grow toward negative infinity. Good. Again, x equals to a is an undefined value of this function, so we never plug in an a into it. So let f of x be a function defined on both sides of a, except possibly at a itself. Then the limit as x approaches to a of f of x equals to negative infinity means that the value of f of x can be made arbitrarily large negative, by taking x sufficiently close to a but not equal to a. Okay, so same as before. So here's an example. Let's plug this into our calculator and find the results for this guy. And let's put -1 divided by parentheses x to the power of 2, close parentheses. So that's this. And now I'm going to go over to my table. So I'll go to my table, delete all the previous values, and again I'm approaching 0. If I just put in a 0, I'm just going to get an error, right? Okay, but we want to approach 0 from either side, so let's approach 0 from the positive side first. So how about starting at 2? I get a very small number. How about 1? Okay, slightly larger number. How about 0.5? Slightly larger. 0.1? Even larger. 0.01. Even larger. 0.000, no, it doesn't have to be 1s. How about 0.00002? I get that number. So this means times 10 to the 7th power, right? So that's a pretty large number. You can see that it's growing toward negative infinity, right? As I let the x values get closer and closer to 0, but I'm approaching it from the right-hand side now, then my output values are growing toward negative infinity. And likewise, if I approach it from the other direction, so let's let x equal to -2, -1, -0.5, -0.4, negative 0.2, negative 0.1, negative 0.03, negative 0.004, negative 0.00007, really, really small. And if I use my arrows to go highlight that little square, I see the actual value, and you can see it's a very large number. 204,081,632, so pretty large. So the closer I let my value get to 0, the larger the output is going to be. Okay, so I'm sufficiently convinced that this is growing toward negative infinity. Let's graph it on Desmos. So at f of x here it is. F of x equals to negative 1 over x squared. And we can see that it is growing toward negative infinity, right? It just keeps getting narrower and narrower and narrower, but it just keeps growing toward negative infinity. So as I let x values get closer and closer and closer to 0 from either direction, my output values are going to grow toward negative infinity. If I zoom out a little bit more, it'll grow down toward negative infinity. Good. Okay. So similar definitions can be given for one-sided limits, one-sided infinite limits. So the limit as x approaches to a from the left-hand side of f of x equals to positive infinity, or the limit as x approaches to a from the left-hand side of f of x equals to negative infinity, and likewise for the right-hand side approaches. Right? So I think that's pretty intuitive, and we have some nice pictures to go with it. So here we have our f of x function, and here we have a case where as x approaches to a from the left-hand side, we see that the function will grow toward positive infinity. So this is the limit as x approaches to a from the left-hand side of f of x equals to infinity. Right? In all of these cases, the blue is the f of x. This function is f of x, and we see that it's growing toward infinity. It's growing that way, toward infinity, as the x values selected grow closer and closer and closer and closer to a, but always from the left-hand side. Based on this picture, we don't know what's going on the right-hand side. It could be that it looks like this from the right-hand side, or it could look like something else. We don't know, but we're only restricting ourselves to caring about the left-hand side for this little definition. So the limit as x approaches to a from the left-hand side of f of x is equal to positive infinity, or f of x is growing toward infinity as x approaches to a. That's another nice way of putting it. Say that f of x grows toward infinity as x grows toward a, but from the left-hand side. Good. Okay, likewise over here, we have x values being selected always from the right-hand side. So they're there, approaching a from the right-hand side. And we see that the output values are again growing toward infinity. Right? So the limit as x approaches to a from the right-hand side of f of x equals to infinity. Or we can also say that f of x will grow toward positive infinity as x grows toward a from the right-hand side. Okay? And then we have the other direction as well. The limit as x approaches to a from the left-hand side of f of x could grow toward negative infinity, or the limit as x approaches to a from the right-hand side of f of x could grow toward negative infinity. Right? And so likewise, we can also put that f of x grows toward negative infinity as x approaches to a from the left-hand side, or f of x grows toward negative infinity as x grows toward a, but from, this is from the right-hand side. Okay, so all four of those cases can be true. So all four cases can be true. And that is, in fact, the definition of a vertical asymptote. The vertical line x equals to a is called the vertical asymptote of the curve y equals to f of x if at least one of the following statements is true. So, of course, if either the unrestricted limit of f of x equals to positive or negative infinity, or one of the one-sided limits is true and equals to infinity. If one of these is true, then we have a vertical asymptote. And so if one of these four cases is true, or the unrestricted one, then you have yourself a vertical asymptote. Let's consider finding the limit of this guy and the limit as x approaches to 3 of this guy, 2x over x minus 3. Okay, how do we find these limits? Well, we have two options right now. One of them is to graph them and examine our graphs, or two, we can use our calculator to find them. So let's use our calculator. So we go over to y equals and put these guys in here. We got 2x close parentheses divided by x minus 3 close parentheses. So here's our function. So let's go over to our table, and we want to delete all the old ones, and we want to approach 3 from the right-hand side. So that means that the input values are always going to be a little bit larger than 3. So let's start with 5, 4, 3.8, 3.6, 3.4, 3.2, 3.1, 3.01, 3.001, 3.00005. There, okay, so we see that they're growing out of control, right? They're getting bigger and bigger and bigger. The closer my input value grows toward 3, the bigger this goes toward positive infinity. So I feel sufficiently confident to conclude that this must be growing toward positive infinity. This equals positive infinity. What about this one? So now let's approach 3, but from the left-hand side. So always smaller than 3. About 0, oops, clear, about 0 or 1 or 2 or 2.1 or 2.4 or 2.7 or 2.8 or 2.9 or 2.9999 or 2.99999, right? So if you use your arrows to highlight it, remember that it runs out of space here, so it rounds. So I didn't type in a 3, I typed in a 2.9999. Okay, and then the output is going to be -6 times 10 to the power of 5. So you can use your arrows to go over there and see that, okay, it's that. So it looks like they're growing out of control toward the negative direction. Good. So just based on this, I feel comfortable coming back up here and saying that this limit must be equal toward negative infinity. They're growing out of control toward the positive direction in this case, growing out of control toward the negative direction in that case. So I know that if I wanted to sketch this, I know I'm going to have a vertical asymptote at x equals to 3. And I know that as I approach this approach 3 from the right-hand side, this is going to grow toward positive infinity, so my function is going to go that way. And as I approach x equals to 3 from the left-hand side, I know that my function is going to grow that way. So that's as much as I can conclude from just looking at this. I don't really know what's going to happen for the rest of this over here. just based on this. So let's just use Desmos to confirm this part of it right here. Okay, so if I graphed it, here's my graph of my function. We can confirm indeed that as x approaches to 3 from the right-hand side, the outputs of my function grow toward positive infinity. And as x approaches to 3, but from the left-hand side, my outputs will grow toward negative infinity. Okay, so that should be enough to tackle the questions or the homework from this section. Let me know if you have any questions, problems, or issues.